And welcome Calculus 2 students. We are looking at the properties of power series. So let's look at what a power series is. Here's our general form. Now our a and c sub k are real numbers and x is our variable. C sub k would be our coefficients and a is the center of the power series. If you'll note down here on a, you'll notice this x minus a. So for this one, the center is a equals 0. Alright, just a special note there so that we can see that one quite easily. That's one that we can see. The set of values of x for which the series converges is the interval of convergence. So we will have to check and make sure that this series does in fact converge. We will check that first, and then after that we will start looking at what the radius of convergence is, and then the actual interval of convergence. So the radius of convergence will just be a number, and the interval of convergence will be a number surrounding that a. Alright, so let's have a go at this. If I look at this first one, you can note my favorite test, the ratio test. Let's look at what this ratio is, and if you'll recall, I need to take the limit as k goes to infinity of my k plus 1 case over my k case, so this is to the k plus 1 over this k plus 1 factorial, and then this is x sub k over k factorial. Now this is the one that I like to rework, so I'll do that. Alright, so my limit here is 0, so this power series is going to 0, which tells me that the radius of convergence on this is going to be infinity, and on either side the interval is going to be going to positive to negative infinity. So the interval is then. Alright, let's look at this next guy. On this one, I need to figure out what test I want to do. The most convenient test would be the root test, and with that I'll have to say that rho equals limit as k goes to infinity for the kth root of this negative 1 to the k, absolute value of, don't forget that, and then x minus 2 to the k all over 4 to the k. In working this, you'll notice that this is just going to be a 1. This is going to be the absolute value of these two. I can then say that this is the absolute value of x minus 2 over 4. I need this value to be less than 1 in order for this to have absolute convergence. So if this is the case, that means that, doing a little bit of algebra, x minus 2 has got to be less than 4, which then means that x has got to be in between negative 2 and 6. So my interval of convergence is then going to be negative 2, 6. And this would then mean that my radius is then 4, with my center being 2. For my next problem, I have to show the absolute convergence. So I will try my ratio test again. So let's see. We need to do r equals limit as k goes to infinity, and I need the absolute value of the k plus 1 case. Over the k case. Doing my little algebra reworking. Alright, forget that I have limit as k goes to infinity of this k plus 1 times whatever my x is, and this thing goes to infinity, which means that my power series, because my ratio then, the only way that I can satisfy this for r being less than 1 is for x be equal to 0. And if that's the case, then my power series itself has a value of 0, and this interval of convergence is then interval of convergence is just that single point 0, and the radius is 0 as well. Now, it would have been more helpful had they given us this theorem before they asked us to do the previous example, because we did a case for all three of these. And now we are to use the ratio test and this theorem to find the radius and interval of convergence. With this, the first thing I'm going to do is use my ratio test again, because it looks like it might follow, and I'm going to find what that limit equals. Alright, in finding this limit and doing my little algebra, this is what I get. This thing is going to 1, which means that because there's no k in this, there is what my ratio test ends up with. Now, for this series to converge absolutely, I know that my ratio must be less than 1, which then means that my x must be between 1 and 3. Therefore, my radius of convergence, so here's my interval, 1, 3. My radius is then equal to 1 with my center equal to 2. Now that we have this, we need to check our endpoints, because this is my interval of convergence for sure, but I need to see if maybe it includes the 1 and or the 3. So let's substitute in to my series. Let's look at for x equal 1. And for x equal 1 we have k equals 1, and this would be 1 minus 2, so that's negative 1 to the k over square root of k. By the alternating series test, we can say that this series converges. I'll write down. Since this converges, I can put an equal to on my 1. Let's try for x equals 3. In this case, my series looks like, and that would be 3 minus 1, so that would be 1 to the k. Ooh, that's just a 1. Okay. And then I have square root of k, so let me rewrite that a little bit. Oops, k equal, got to put that in there. K equal 1, this will be 1 over square root of k. This is a p series, with p being equal to 1/2. This thing diverges. That means my interval of convergence is just this right here, not including the 3, but including the 1. In Theorem 10.4, we are able to combine different power series using this theorem. So very similar to what we do with limits, and just an extension of what we have been doing. So if I look at this a here, I notice that I have an x to the 5th over the power series that they have given me. So I can see that this thing could be rewritten as x to the 5th times all of my series here that's sitting out there. So that would be 1 plus x squared plus blah blah blah. That means that this thing is then x to the 5th plus x to the 6th plus... So I could rewrite this using this format as just xk plus 5. And then I would get that series sitting there. Now, if I'm going to look at this one, I'm supposed to find the power series. There's the power series. And then they want the interval of convergence. So this has a ratio, my r in this case, equals x. Now I need for that x, or that absolute value of that x in particular, to be less than 1. Okay? So this means that my interval of convergence is then absolute value of x is less than 1, or you could say it's from -1 to +1. On this next one, I'll use function composition and just say that this 2x is my x, so I'll just substitute that way, and this makes this easy. I could just say that this is 1 plus 2x plus 2x quantity squared, just following from this right up here. And that would mean that this thing written as a power series would just be the function composition of that, which is just 2x to the k. Now, in order to find our interval of convergence, I'll have to say that this is a geometric series whose ratio, r, is equal to 2x. So this thing is going to converge provided that this ratio is less than 1. Or, doing a little algebra, I need to say that my absolute value of x must be less than 1/2. In other words, my interval of convergence is -1/2 to +1/2. This is another one utilizing property 3, or function composition. So I'm going to say that this is equal to 1 plus -x squared, because it's off by a sign, plus -x squared quantity squared plus blah blah blah. I can write this as a power series then by just saying that this is -x squared to the k. Now, if this geometric series is to converge, that means that my r, which equals -x squared, this absolute value must then be less than 1, which means that absolute value of x must be less than 1, or my interval of convergence is another -1 to 1. The next theorem talks about differentiating and integrating my power series, and a lot of these properties carry over provided I stay within that interval of convergence. So we're going to look at a couple of examples of this. First up, they want us to integrate. So I'm going to integrate this f of x, see what I get, and then I'm going to integrate term by term, and I'm going to find what that power series represents. Alright, I found my derivative and I found my power series notation. So this means that we have f prime of x equals 1 over 1 minus x squared, which is then equal to this power series. I need to slow down. K plus 1 x to the k. This thing converges, and it does so on the interval x is less than, absolute value of x is less than 1, or from -1 to 1. So this is our interval of convergence. Let me check my endpoints, my 1 and -1, and see what happens there. Alright, we found that at both endpoints it diverges, so this is my interval of convergence. In the B part, we're going to go the other way with this, and we are going to integrate our 1 over 1 minus x dx, and we're going to integrate this, and then we're going to integrate our function term by term and see what power series we get. Alright, now I'm going to equate these two, and I'm going to say that negative, the natural log of this 1 minus x. Now we're going to have to choose that x be less than or equal to 1 for this, because that is our, oops, just strictly less than, because it diverged at the endpoint, strictly less than 1, because, oops, I did it again, sorry, negative 1, because that is our interval of convergence. So this thing here is then going to be equal to this x plus x squared over 2 plus x cubed over 3 plus some constant. Now this guy's constant, I just threw over the other side and squished it together. So what I'm going to have here is just the natural log, and I'll move that negative over to the other side, of 1 minus x, and that'll make it easy for my power series. I'll just make it equal to negative k starts at 1 and goes to infinity of x to the k over k. And that's what we get for our integration of this little fella. Go to the next. For our next example, we're going to utilize the fact that tangent minus 1x is equal to this integral. Therefore, we can, if you'll recall from a previous example that we did, I think example 3, we know that 1 over 1 plus x squared is equal to 1 minus x squared plus x to the 4th minus blah blah blah, as long as our x, absolute value of x, is less than 1. So if we integrate both sides of this, we'll see what we get. And that made this one really easy. I now have this series, and I can make sure that both sides agree. You know, choose your starting point at x equal to 0. Make sure that that works, and it does. Both sides are equal to 0. So therefore we can choose c equal to 0, make this a little simpler for ourselves, and then we can say that tangent minus 1, right, it's alternating, so negative 1 to the k, and our x's are odd powers, so we're just going to write that as x to the 2k plus 1, our odd power guy, and then I have odd numbers in the denominator, so that's another 2k plus 1, and this thing converges for x less than 1. I need to test the endpoints of this, see if this works, and if you test the endpoints at both 1 and negative 1, you will find that both endpoints converge, so I can say the interval of convergence is negative 1 to 1 inclusively. For this one, because I know something about natural log of 1 minus x, we already did that one, and I'll be able to rewrite this. I'm going to use my log properties to say that this is natural log of 1 plus x minus the natural log of 1 minus x. And this is the one that I actually know something about from a previous example. So let me write down what it is that I know. Okay, so there's what I know about this guy. This one I can use that composition and just say that that x is really a minus x and replace those values. So I'll write down what I've got. If you'll notice, this wipes away all of my even guys and doubles up on the odd ones. So this is going to be 2 times x plus x cubed over 3 plus x to the 5th over 5 plus blah blah blah. And this can then be written as 2 and k equal 0 to infinity as x to the odd powers, so that's 2k plus 1. And in the denominator I have those odd guys again, so that's 2k plus 1. Both of these converge on this interval. Absolute value of x is less than 1, and therefore my new series does too. And that's all for this particular section.